To introduce our next keynote speaker for the day, Nicholas Mandrak. Nick is going to be discussing potential effects of climate change on aquatic invasive species in the Laurentian Great Lakes. Nick is a professor in the Department of Biological Sciences at the University of Toronto Scarborough and director of a professional master's program in conservation and biodiversity. His research lab examines the biogeography, biodiversity, and conservation of freshwater fishes. Nick is a research associate with the Royal Ontario Museum and the South Africa Institute for Aquatic Biodiversity. He has co-authored more than 300 scientific articles and reports and several books, including the upcoming second edition of the ROM Field Guide to Freshwater Fishes of Ontario. So welcome, Nick, and you can take it away from here. Looking forward to your talk.
Thanks, Mackenzie, and thank you everyone for joining. When I was invited to give a talk on climate change and aquatic invasive species in the Great Lakes, I readily agreed, as I have looked at this question since my undergraduate research. My lab is currently conducting research on the synergistic effects of climate change and aquatic invasive species on the native fishes of the Great Lakes. But a 35-year-old undergraduate thesis and some ongoing unpublished research projects do not necessarily make for a good high-level overview talk. So I initially turned to Frank Rahal and Julian Olden's 2008 paper on assessing the effects of climate change on aquatic invasive species for an organizing framework for my talk. I then checked with Julian and did a literature review for a more recent framework, but didn't find one. Therefore, my talk will be organized according to this framework, illustrated with research from my lab, the literature, and some speculation on my part. So you can see that in this framework, the authors have identified some major interactions between climate change and aquatic aquatic systems, including altered thermal regimes, reduced ice cover, altered stream flow, and then increased water development and increasing salinity in some circumstances. And then identified 4 ways in these impacts may interact with invasive species. So those include influencing the establishment and spread of invasive species, altering pathways of species introductions, mediating impacts, and influencing control strategies. Now, note that I actually think there's a potential 5th effect not included in the original framework, range expansion, because I think we will need to decide if we treat species expanding their range under climate change as invasive species and manage them accordingly. Now, as my lab conducts research primarily on fishes, I've largely restricted my talk to invasive fishes, but the framework would apply to other aquatic taxa as well. So we look at this first potential effect, influencing the establishment and spread. So at the courses level, invasive species become established in an invaded ranges with climate similar to that of their native range. And this is the premise for climate match and species distribution models that are used to predict the potential distribution of invasive species. And in the simplest sense, this is related to basically the thermal tolerance of the species, and in terms of aquatic invasive species, water quality and quantity. And you can see here the potential effects of temperature on the water temperatures and oxygen levels, particularly in the winter, and then potential changes in precipitation effects on flow regime, salinity, and riverine habitat. And then in reality, though, the influence of climate is multifaceted, and there are finer filters than climate itself, including habitat and ecological interactions. So climate change may influence the filter to this point, you know, that change would be related to warmer temperatures, reduced hypoxia, altered flow regimes, harsh salinity, and the move from riverine to reservoir habitats. Now, we can look at this very simply. Here's an example of the potential winter survival of red-bellied piranha in North America, and it's believed that the red-bellied piranha as of 1997 could have survived to a winter isotherm of about 12 degrees, and under a climate change, the isotherm, with under a 2-degree increase, theoretically that isotherm moves this much further north, and there's much more of the southern United States that would allow the overwinter survival of piranha. And I'll just point out, this is an old cover from the Toronto Sun, and we have collected piranha in Canada and in Ontario, and have always thought that, given this scenario, they just wouldn't be able to survive over winter, even under a climate change. But my point here is we can look at this climate match very simply in this manner, or as we've done using more complex maximum entropy models, where in this case we've modeled the potential distribution of Asian carps based on climate, and any species distribution model that is based on climate has the potential to be modified in order to predict what the potential future distribution under climate change might be. And I do want to show you some work that that Justin Hubbard in my lab recently completed as his master's thesis and is currently prepping for publication. And in this case, these are about 426 freshwater ecoregions of the world. This is the Laurentian Great Lakes right here. And this is under our current climate. This shows how similar a climate match the Great Lakes are to all the other ecosystems in the world. And what you see is, yeah, we have a great climate match to Europe. Not surprising, that's where a lot of our Great Lakes invasive species come from. And as you get into more tropical areas, there's a lower climate match. It's the same with more polar areas, right? But then Justin applied a future climate change scenario to this model and showed that there are more areas of the world, such as the southeastern, southwestern United States, portions of South America and Southern Europe and New Zealand, that are going to become more similar to the Great Lakes, and hence those areas of the world may be potential new areas as new donor regions for invasive species to the Great Lakes, should there be a pathway to actually get them to the Great Lakes. And however, you notice there wasn't a lot of areas of the world that were similar, and this is another analysis that Justin has done, and what it basically looks at is the redder the area, the more similar the area is becoming to the rest of the world under a climate change scenario, and meaning that it's at a greater risk of being colonized by invasive species from other part of the world. And you can see that for the Laurentian Great Lakes ecoregion right here, there isn't much change. So there is a little from those areas of the world that I pointed out, but it's not nearly as severe as we see, for example, in the Canadian Arctic, which is going to become much more similar to other areas of the world, and as a result be much more invadable and by invasive species that could become established there. Now, Sarah Campbell, a recent graduate of my lab, developed a trait model to predict future invasive fish invasions of the Great Lakes, and she did it under she initially developed it and published it in 2021 under the current climate scenarios. And actually, she backcast to the last 100 years. And what we did is we actually combined Justin Hubbard's climate models with this trait model to look at how changing climate matches for 34 previously failed Great Lakes introduced fishes would change under a climate change scenario. So basically, but we know of about close to 70 species that have been introduced into the Great Lakes. About half of them have become established. The other half have failed. So we know that there are pathways for these species. So we looked at those that had failed, and many of them had failed in the past because of a lack of climate match. Well, if now we apply the future climate scenario, we see that 14 of those 34 species now have a higher probability of establishment because of an increased climate match. And only 4 actually have a lower probability of establishment because of a decreased climate match. And you can see some examples of these species here. This is the historical prediction for climate match in the future. So wherever it's redder in the future, like for mosquito fish and yellow bass, than it was in the past, that means that the Great Lakes are becoming more, have a higher climate match for those species, and the probability of establishment of those species increases. This paper is, by the way, currently in press in Biological Invasions. And then, well, of course, the species that everyone is concerned about in the Great Lakes are the Asian carps, and the nature of their spawn actually makes them quite sensitive, or potentially sensitive, to climate change. And so, in a nutshell, Asian carps need to grow over several years in warm environments in order to mature. And then within the year that they mature, they have to grow their water temperatures have to be warm enough that their gonads mature, and then they have to be attracted by high flows to rivers where they spawn, and then they follow. They migrate up the river. Then they spawn, and then the fertilized eggs have to drift down the river at the right speed and temperature to hatch before they actually reach the lake. If the eggs reach the lake before they hatch, they're not viable. So you could see how Asian carp spawning is particularly sensitive to the 2 key elements of potential climate change: temperature and water quantity. So here's an example of we've modeled how successful spawning might be. So the blue is the average water temperature for this station on the Thames River in southwestern Ontario. The black line represents the average water velocity over this 8-year period. And so we can actually convert this into when would spawning be suitable for Asian carps. And I just want to point out this line. This is the line, the earliest at which, based on these water temperatures, that any Asian carp species would be mature enough to actually initiate spawning. And at this point, then you want to see a little rise you would need a little rise in the velocity, like a flashy storm event, in order to trigger migration. And then the eggs would be dropped, and then they have to drift downstream. So we can actually convert this into the length of river required for suitable spawning. So when we do that conversion, you can see that here the length of river is relatively long, but it's irrelevant because they have not matured within the year to spawn. But right when they've matured, given the combination of temperature and water, the eggs need only drift 15 to 25 kilometers, and that can be readily done in the lower Thames River that is free of barriers. And then you can see later in the year when we have some of these peaks in fall flows, again, the river length is relatively short, and spawning would be viable. We've actually done this for about 100 tributaries in Ontario, and identified that a lot of them are actually suitable for Asian carp spawning. Green is not suitable. Well, yellow is not suitable. Orange is suitable, and red is highly suitable. Now, what I've just explained to you is a very simplistic model of Asian carp spawning. Basically, it just assumes that the egg is dropped and it just flows straight down the river using like a 1 or 2 dimensional flow model. But we know that rivers are 3-dimensional, and that there are eddies and backwaters and so on. So a simple linear model may not sufficiently characterize whether or not spawning would be successful. So Thage Hare, a recent PhD graduate from my lab, actually did detailed 3-dimensional hydrologic modeling of Asian carp spawning in the Sandusky River in the Lake Erie drainage, where grass carp is established. And he actually did it during a USGS dye experiment, so they could see where the dye went once they released it to simulate a spawning event. And that dye event actually occurred during an actual spawning event. So Thage could end up developing a model that was truth by actual spawning. And so we're pretty sure that at the time Asian carps were spawning at this dam here, and then the eggs would drift down here, and if they drifted all the way down and they hit Muddy Creek Bay, the eggs would fall out of suspension and they would be buried in the sediment and not hatch. But if the temperature and flow conditions were right, they could potentially hatch somewhere in the stream, and that's what Thage was trying to model. So here's an example of one of his models. So this is where they're spawning, and then the eggs are going to move through here. So this is an actual simulation of eggs, the movement of eggs through the Sandusky River. And so this is where eggs were actually captured during this experiment. And if they're captured here, they were shown to actually be viable and likely to hatch. And so Thage, let's see if this model, it's not going to work. Hold on. Give me 1 second. I'm just going to turn off my pointer for a second. Sorry. Well, unfortunately, it worked when I was practicing, but it's not working now. Let me try it one more time. Oh, now it's working. So now you see the eggs being released in the model and going downstream and then entering the area where the eggs were captured. So if at the end of this simulation, there are some eggs still in this area, that means that successful spawning could occur based on this model. Any eggs that end up here, which is a lot of them, will likely drop out and be buried in the sediment and not be viable. So this model, using temperature representing that influences the hatching rate, and the actual flow at the time of the spawning event, is used to determine whether or not that spawning was successful, and the conclusion was that it was. Now, Thage actually took the same model and he actually changed the temperature based on what you might expect under a climate change to see how that might influence the spawning and whether or not there would be higher or lower hatching success. And so this is just a summary of the results here, and you don't need to see too much or read too much into it, but this is a climate change scenario that he used. for 3 time periods. The next, basically 40 to 60, 2060 to 2080, and then 2080 to 2100. And what you see across the board is this is change in hatching time. Hatching time actually decreases, which means that the eggs will hatch quicker, which means they'll more likely be in the river when they hatch. And then you can look at what the hatching rate is, that is percent survival. And you see that at certain times during this model that went between July 10th and July 13th, the hatching rate is much higher under a climate change scenario. So the take-home message is climate change is likely going to increase the successful spawning of invasive species such as Asian carps in the Great Lakes. Now, the second potential effect of climate change on aquatic invasive species is the pathways of their actual introduction. And, under climate change, pathways may be altered for a variety of reasons, including physical, biological, and social economic reasons. And if we look at the history of the invasive fish pathways in the Great Lakes, we see that the most important pathway throughout time until recently has been authorized stocking. And you can see starting in the 1980s, managers started realizing stocking exotic species in the Great Lakes is probably not a good idea. And then when you look at some of the other important pathways, you look at this red one, live trade. And what you can see is there's the trajectory upward for live trade and species becoming established in the Great Lakes as the result of release from live trade, such as the aquarium trade, the water garden trade, the bait trade. So this is the pathway that's more likely to be providing additional invasive species to the Great Lakes going to the future. And the one other one I want to point out is commercial shipping. And you can see it here, the purple started particularly post-World War II when shipping increased, and it increased for a while here. And it's gone up a little bit since the 2000s, and then it's plateaued again. And I'll talk about that in just a second. So when we think about ballast water and shipping, there may be changes to shipping patterns. For example, Pacific ports may become connected to Great Lakes through the Northwest Passage under climate change. Miller did a study about a decade ago that was more of an economic study of shipping and looked at the potential impact of climate change on shipping and showed that the lower water levels expected in the Great Lakes may increase the cost of shipping, which may actually reduce shipping in the Great Lakes and potentially reduce the release of aquatic invasive species into the Great Lakes. However, that might be offset by the fact that there's a longer ice-free period, which may lead to a longer navigation season. And Millard specifically pointed out that there may be this increased AIS risk because of the longer navigation season. And that would lead to increased control costs if we decided to control those invasive species. However, given what has occurred over the last 20 years in terms of ballast water regulations, those regulations may actually be reducing the risk to the Great Lakes, regardless of climate change. Now, in terms of the live trade, I've already showed you Justin Hubbard's work where more areas of the world will become more similar to the Great Lakes. And if species from those areas of the world are in live trade, such as the pet trade, they may become established if they have a greater probability of becoming established if they are introduced into the Great Lakes. As Sarah pointed out in her research, more species and trade can survive in the Great Lakes. A couple of years ago, we looked at the pet trade globally, and not just for fishes or aquatic species, but the one thing that struck us was that the demand for exotic pets is increasing, and it's forever changing, largely due to market demand. Apparently people are always looking for new pets, because and wholesalers are always looking for new pets, and retailers, because new pets are novel and are worth more. So there's this ongoing and changing demand for exotic pets. Climate change may influence their distributions in their native range. That may make them more accessible to commodity change, that is collection and then moving through the pet commodity change to ultimate end user locations. And global shipping and air pathways may be influenced by climate change as well, and that may influence what species and live trade may end up in the Great Lakes Basin. Well, there's also this question of canals and other connections. And a few years ago, in response to the concern about Asian carps moving into the Great Lakes, the U.S. Army Corps of Engineers evaluated all the potential connections between the Mississippi Basin and the Great Lakes. And most of them were determined to be low risk, except for, of course, the Chicago area waterway system, most notably the Chicago Shipping and Sanitary Canal, that was a connection between the Mississippi Basin and Lake Michigan, and is the connection through which we know in the past invasive species have moved through. Now, that connection is now less risky because there are 3 sets of electrical barriers there, minimizing the movement of fishes between them, although the risk is not eliminated. There are other connections that remain unimpeded, such as in the Erie Canal, that connects the Great Lakes Basin to the Atlantic Coastal Basin. And there's also the Welland Canal that connects the Lake Ontario to the upper Great Lakes. And a study that I did a few years ago with Jae-Woo Kim showed that through tagging that fishes can readily move through the Welland Canal between the basins. Now, how do we relate this to climate change? Well, I think it's related in a couple of ways. It's related to ballast and the operations of these connections. And there's risk related to the uncertain future of shipping volume, as pointed out by Millard, and there's uncertainty related to how some of these waterways will be operated in the future, just from a shipping perspective. And we also know that some of these waterways, smaller connections along this watershed, are areas of that are connected only when flooded, and when there's increased flashiness under climate change, these areas may be flooded more often, and that could further create connections that we don't currently have. Well, as I pointed out before, authorized stocking, we really don't introduce non-native species to the Great Lakes anymore, right? But people still want to illegally stock species that they're interested in, either farming for aquaculture or for catching. And a good example of that is tench, that was introduced into the Richelieu in the 1980s and is now on the doorstep of the Great Lakes. And it was introduced because a farmer wanted to establish an aquaculture facility for tench. Now, the thing about climate change is it's going to allow species that don't currently have a climate match to the Great Lakes to be able to survive in the Great Lakes. And when you see pictures of this Wells catfish, you know that there are going to be anglers in the Great Lakes saying that's exactly what we need in the Great Lakes. Or this African sharp-toothed catfish that I'm holding is probably one of the most invasive fishes in the world that has been introduced to every continent. May not be a climate match to the Great Lakes now, but maybe under future climates. So illegally stocking species that are now have a better climate, will have a better climate match to the Great Lakes than in the past is definitely a potential risk, but a hard one to quantify. A third way in which climate change may affect aquatic invasive species is it may mediate impacts of AIS on native species. And we know that those impacts, even outside of climate change, can be direct in forms of competition, predation, or hybridization, or indirect in terms of habitat alteration and destruction. And I'm just going to give you a few examples here. So, in a pretty straightforward way, and this is a classic paper done in the Rocky Mountains to show the potential competitive interaction between invasive brown trout. Well, they're actually they're both invasive species in the Rocky Mountains, but in Eastern Canada, the brown trout would be invasive and the brook trout would be native. But you can see how here we have the food items eaten and the water temperature, that under cold water conditions, brook trout feeds at a higher rate and would likely outcompete brown trout. But then when the water temperatures start increasing, brown trout consistently outcompetes brook trout. And this is certainly something that has also been seen in the Great Lakes Basin, but this is occurring already without climate change. And however, climate change may further alter the competitive interactions between invasive and native species. And I want to give you an example of research that Megan Kindry in my lab is working on. And she's looking at this question of white sucker in Lake Ontario. And white sucker, historically one of the most common species in Ontario and the Great Lakes Basin. Their catch per unit effort declined dramatically in Lake Ontario after the introduction of the round goby. Well, they're both benthic species, so the obvious concern is that round goby is outcompeting white sucker. And white suckers are important because they act somewhat like Pacific salmons, in which they live out in the lake, they feed out there, and then they bring that energy with them, then they spawn in streams. And they don't necessarily die every time they spawn, but they're releasing eggs that are based on energy from the lake in the stream. And when they eventually die, often after spawning, their flesh will add nutrients to the stream as well. Well, again, not considering climate change, Megan just looked at the diet overlap between the species in several Toronto area rivers, and found, yes, there's a high diet overlap. Then she said, well, okay, under current circumstances, they're already competing with one another. What will happen in the future under potential climate change? So she looked at the thermal tolerances of the species in the field, where she actually did the critical thermal maximum experiments using this equipment streamside. And what you can see is basically round goby has warmer thermal preference or tolerance than white sucker in all of the streams. So, that would make us think that, if the streams get warmer under climate change, that round goby would likely do better, and white sucker not do so well. But this is that's just inference from this pattern. So she actually did a follow-up set of experiments where she looked at the feeding rate of the two species in the lab over different temperatures. So this is not unlike that brook trout brown trout graph that I showed you earlier. And what you see is consistently across these increasing temperatures, round goby feeds at a higher rate than does white sucker, which would mean that they would consistently outcompete white sucker at any temperature. Then she thought, well, climate change is not going to only influence temperature, but flow, and white sucker, based on the literature, appears to have greater tolerance to higher flows than round goby. So she did the same experiment, and this time, rather than having temperatures here, we just have experiment at two temperatures, 22 degrees C and 25. But these are increasing velocities, so increasing flows in a flume in the lab, and we look at the number of prey consumed. And what you see here is, again, under low velocities, round goby is clearly outcompeting white sucker until you get to the highest velocity, where white sucker appears to be better adapted to these high velocities, and there's no significant difference. And the same is seen at the even higher temperature of 25 degrees C. And Megan's take-home message, as she summarized to me in an email yesterday, is white sucker are pooched under current and future climate change scenarios unless they can find high flow refuges. However, we expect those high flow refuges to become less common under climate change, where streams will become flashier, but overall water quantity will likely decrease, and hence the flow will decrease. So I have another student looking at a similar question, but in this case, it's interesting that there's two populations of round goby in the Credit River. One in warmer water, average summer temperature of 19 degrees in Mississauga, and one in the headwaters in Hillsburg with average summer temperature of 14 degrees. And in this case, she did an experiment where she basically constructed functional response curves. She did it between three benthic species: the invasive round goby, the native black-nose and long-nose daces. And so basically, what we see here is this is the number of prey consumed based on the prey density. And basically, the higher curve, the better you are at feeding, right? And then when you put the three species on a single graph, the higher the curve, the better competitor you are. So in this case, under these temperatures, round goby outcompetes the natives in both Hillsburg, at the lower temperatures in Hillsburg and in Mississauga. Now, again, Kylie did these critical thermal max experiments like Megan, except she did them in the lab, and showed that actually their tolerances are not that different. And then she actually looked at, in this case, these colors represent temperatures, and then we have three plots for goby, black-nose dace, and long-nose dace. So we're looking at how they would interact with one another under these higher temperatures that you might expect under climate change, in areas that are currently cold water, and then the areas that are currently warm water in the summer. And again, basically the message is round goby is going to outcompete at current and future climate change temperatures, both in colder and warmer waters. And then, frag has been talked about quite a bit over the last couple of years, and it's an example of a species that alters habitat for native species such as fishes, particularly some of our endangered wetland fishes. And those it was shown by this study that lower water levels that were likely related to climate change facilitated the faster spread, or the rapid spread, of Phragmites since about the year 2000 in Long Point Bay. And there's similar examples in other Great Lakes as well, or areas of the Great Lakes as well. And I'll just leave that here. I see I'm coming to the end of my time. Last couple of slides here. Climate change may also influence control strategies. For example, in terms of monitoring, lower water levels and lower volume could lead to higher detection probability of conventional and eDNA sampling, higher detection probability of aquatic invasive species such as fishes. However, flashiness may make sampling more difficult and may disperse environmental DNA farther from the source. Climate change, climate change could also result in faster population growth, which would mean less time for early detection and rapid response. Here's an example from Eric Dean's research in my lab, where he shows that age of maturity decreases with increasing annual summer temperatures. So when you have a lower age of maturity, your population grows faster. And here's an example of, this is the fishway at Cootes Paradise between Hamilton Harbor and Cootes Paradise at the western end of Lake Ontario. This is meant to prevent carp from going from Hamilton Harbor into Cootes Paradise. And it's been shown to be a really good control measure for those carp. However, in 2019, when there were record high water levels in Lake Ontario, likely related to climate change, this barrier was actually flooded. And there happened to be tagged carp, common carp, in Hamilton Harbor at the time. And you can see that several of those carp were detected in Cootes Paradise and very likely got there as the result of the control barrier being flooded. And then these types of barriers may do better under lower flows and volumes, but they may do worse under higher flows. Also higher temperatures may make bubble and CO2 barriers less effective as their saturation decreases with higher temperatures. Last slide or two. What species will disperse into the Great Lakes or from one Great Lake to another under climate change? Well, I showed you those connections between the Great Lakes and the Mississippi and Atlantic coastal basin. The risk is lower because of what's being controlled there, but it's not gone. And if species were to move into the Great Lakes from the south or between Great Lakes, should they be considered aquatic invasive species or climate migrants? Is there a difference? And I mentioned to you that I actually studied this for my undergrad thesis like 35 years ago, I hate to say. And I developed a rudimentary trait model. And I basically predicted that 27 species that have their thermal limits just south of the Great Lakes likely could disperse into the Great Lakes. The unfortunate thing about being around this long is that I can actually test my prediction with time. And my predictions were have largely not come to fruition, which I think is a good thing for the environment. Not a good thing for supporting my model, though. And finally, here's an example. There's a flathead catfish invasion of the Great Lakes that is likely being precipitated by climate change, where they started off here in the 1800s, and now they're found all throughout the southwestern Great Lakes Basin. And I will end there.
Thanks so much, Nick. That was a great and very informative presentation. I really appreciate that. We did have one question come in, so we'll squeeze that in before we close off the session this afternoon. We have a question from Francine. She says, I was intrigued by the reassessment of failed fish invaders in the new climate change scenarios. Based on the figures, it looks like tench may be less likely to successfully invade. It looked less red in the future. Any comments on why tench may respond less favorably to climate change?
Yeah, it's because climate change is not the only element that goes into that model. It's also the traits of the species that we expect to invade. So undoubtedly, tench are going to make it to the Great Lakes, and in fact, right now they're further north. They're actually dispersing southwest into warmer climates. So climate itself will not be a barrier to the Great Lake. invading the Great Lakes, but rather it will be the composition of species that we might see in the future that might provide some ecological resistance to tench being a successful invader. However, I really think that tench invasion is so close that we won't have any of these additional invaders in place before they make it to the Great Lakes. So I just don't think there will be that ecological resistance. But in theory, that model suggests if those other species were in place in the future, that tench would be less likely to invade.
Right. Okay, great. Thanks, Nick. There were no other questions, so if anybody has any further questions for Nick, you can shoot us a message and we can pass it along. So thank you guys so much. Before we close, I am just going to share my screen for a moment and give a little plug to the Invasive Species Center's microgrant program. The deadline for submissions is this Friday, February 4th. So I just wanted to share that quickly before we close off our keynote plenary for this afternoon, to get your submissions into the microgrant program before this Friday. So with that, we will close our keynote plenary session, and please join us back again at 2:45 in about 13 or so minutes, where we're going to start our last session of the day on aquatic invasive species research and management developments. So I will see you then. Big thanks to Nick and Rob for their wonderful keynote plenaries. I'll see you guys soon.